Yeah, okay, so let's continue. So now we are in it's a path integral, but it's a path integral on the lattice. That's why we say, as Francesca already told you, it's very similar to the lattice QCD. Why it's very similar to the lattice QCD? You know how we make path integral regulars. Because if you still remember for the path integral, we have the integral over trajectories, we have this capital D with our phase space variables. But on lattice theory, we don't need to use capital D, which is the infinite production of single variables at each time. Now we have a discrete integration, which gives you the n-dimensional integral. The n is related to your the number of lattices. So that makes the path integral on continuum space-time a regular definition, which becomes a multi-dimensional integral. And what we have just show is that we already write out this integral, which is a spin-form model on some space-time lattice. So it's a regular defined integral. So to calculate the amplitude, of course, is again a hard task. So it's basically to evaluate out this integral. And its dimension can be calculated from here, for example. So what variables we have, for example, in one vertex, how many variables we have? We have the group elements. We have 5, but because of this, sorry, I jumped to here. So we have the variables, which is GVE, we have 5, and we have ZVF, which we have 10. These are the variables we have. GVE is SR2C group elements, but we have this gauge transformation, which will gauge fix 5 into 4. And we have ZVF, which are spinors, and we have this gauge transformation, which gives you that ZVF has 2 degrees, have 2 variables for each ZVF, and we have 6 for each SR2C group elements. So how many variables we have? We have 4 multiply 6 plus 2 multiply 10. That's all the variables we have for one vertex. This is only one vertex, so one space-time lattice. And this is 44. So even for one vertex amplitude, we need to do a 44-dimensional integral. So it's already a bit complicated. So 44 dimension for one vertex. So, but luckily, we know our S can be written as some spin, summing of phases spin with some other part. So it's linear in spin. So when we have large spins, which is the asymptotics, we have the saddle point approximation, which usually we used to derive the path integral in quantum mechanics and quantum field theory. And this makes it possible to do all the calculations perturbatively. Perturbative in terms of the J. And also, as Francesca already told you, Gf goes to infinity is somehow h bar goes to 0 is the classical limit. And that's why perturbative in J is also perturbative in h bar. That's why this is a perturbative calculation using the saddle point approximation. So what is, I think I don't need to introduce the saddle point approximation as you already learned it during your quantum mechanics class. One important thing, of course, is to find the saddle point. What is the saddle point? It's the solution of the equation motion. That also tells you why, in the classical theory, the path integral is picked on your classical trajectories because it's given by the solution of the equation motion. Of course, now the equation motion is discrete because we are on a space-time lattice. All the variables are discrete. So we still have our action. I just copied here. It's not so complicated, but a little bit complicated. Okay, and now we know what is the the equation motion is coming from the variational principle of the action. And here we have, so if you still remember the basic variables are G, the group, the G, the group element, and also the Z, which is the spinors, CP1 spinors, and the SL2C group elements. And now we just need to do the variational principle. But before we do variational principle, we have a spatial relation of this capital Z defined using the smaller z. And this actually introduces a relation between the capital Z. So if you want, because this smaller z only defines on the F labels, it doesn't define on the E labels. E label is the edge, F is the faces. And each face in one vertex is given by the two edges. So we have a relation first between this E and E prime, the two edges. And then we can do the variational principle with the small z. And this, again, gives you a very similar formula. So if you look at this is the first equation. And this group element is on the left. And if you look at the second one, the group element is on the right. And this set, of course, is a spinor, because it's our fundamental representation was SR2C multiply a spinor, is still a spinor. So we got, this is more or less a parallel transport, is a group action on spinors between the edge E and the edge E prime. And here is a similar thing. It's edge E and edge E prime. There are some typos, sorry. And then we can combine the two equations. How to combine the two equations is becoming this, sorry. It's becoming this. So it's a group action, SR2 group action on the bar vectors, actually. And how to define the bar vector, you can find that if I use, if I define this set and that tilde is coming from the variational principle. And this actually forms a bar vector, which is the element of the lead algebra of SL2C. So this is a bar vector. And this equation becomes a parallel transport equation on bar vectors, which are the parallel transport equation on the Lie algebra of the SL2C group elements. And finally, we can do a variational principle to the SL2C group element. What we obtain is what we call closure condition is also closure on this bar vector we defined here. So the closure is the spin multiply the bar vector, they summing over at each edge. So we have 4 on each edge corresponding to the 4 faces of the tetrahedron if we want. This is the Minkowski theorem if it's a tetrahedron. Here, we don't see it's a Minkowski theorem because we are lacking a geometric representation, because if it's a tetrahedron, we also need an extra condition. The extra condition is, sorry. The extra condition is there is a normal which multiply all the bar vectors on that edge is equal to 0. This means it's actually a 3D object instead of 4D object, because tetrahedron is a 3D object. So when we embed it into the 4D, it has a normal. It's a 4D normal of this tetrahedron. But from these two equations, we don't get this extra condition. So we only get a parallel transport condition tells you that actually on each vertex, we have a bar vector, and these are 10 bar vectors for each face. This bar vector doesn't depend on the E because it's a parallel transport. And it's subject to closure. So we have 10 faces, 10 triangles in the space-time. That's the geometric explanation of this equation motion. One more thing I want to say is this equation motion, you can also try to find a complex solution. The reason is if you look at the form of these equations, they are polynomials. They can written as the polynomial equation of your basic variables. And we know polynomial equation always have solutions, and the order of solutions is given by the algebraic variety theory, how many solutions they have, of course, many of them will be complex. For example, if we have the second order polynomial, we know when we have the real solution, when we have the complex solution. For the third order, it's more complicated. We have 3 solutions, and many of them will be complex. And now we have more equations. We have 44 variables, 44 equations. It's really complicated to determine. But in principle, we have many solutions, and most of them will be complex. But the most important thing is when we get real solutions. And there is a condition for the real critical point, and this is the dominating critical point, because you can show the real part of the action is smaller or equal than 0. And the dominating critical point happens at the real part of the action equals to 0. And this condition tells you your bivector, so this the defined bivector is nothing else but given by the boundary C. So, and this also makes the closure condition trivial if your boundary C forms the tetrahedron, because if you remember, C is related to the 3D normals of your triangle with your bivector. So this gives exactly a geometric meaning of the equation motion, in the sense that for the real dominating critical point, this bivector defined here actually doesn't depend on the word on V, and it's just a rotation of the sigma 3. Sigma 3 is a boost. The store is the bivector for the z direction, for the third direction of x, y, z. So now we have a geometric notion because, as I said, now we can find a conormal of this bivector on each edge. The conormal is nothing else but the time direction, because this is purely located in the space. And now you can show that this equation motion described exactly a 4 simplex. Why it's described as 4 simplex is now we have 10 bivectors, and each 4 bivector of them forms a tetrahedron. So that's why. So why it forms a tetrahedron, as I said, so we have the closure, which is the Minkowski theorem of the tetrahedron, and also we have the conormal of the bivector for each E, for each F in E, sorry. And this too determines a tetrahedron. And since in total we have the parallel transport equation, which gives you in total only 10 faces, this means this 5 tetrahedron, so we have 5 E's, 5 edges. This 5 tetrahedron forms a 4 simplex. So you can show this is exactly the thing that describes the 4 simplex. That's why we see, so we start from a triangulation, and then we go to the abstract graph. We don't know what is the geometric expectation of our amplitude. But finally, from the classical equation motion, we recover the geometry from the door graph. And this is really tells you that it describes some geometry. That's the geometric meaning in the classical limit. So this tells you that already classical critical points is given by the 4 simplex geometries. In other words, if we give you some 4 simplex geometry, you can write out the spin-form critical data from that. This is the thing. So basically, this is one part of the numerical program you need to do, because when we give some classical geometry, we want to note the spin-form amplitude. But now we know that the 4 simplex geometry is exactly corresponding to the real, is exactly no degenerate real critical points. So when we give out a classical 4 simplex geometry, we can already write out what is the critical data for them. And this can be written in the following way. So we have the 4 normals of the 5 normals of the tetrahedron. As we said in the first slides, if you still remember, a 4 simplex can be given by 5 normals. And we cut the normal, we get a 4 simplex. And these 5 normals is given by the rotation. This is SO31. Sorry, SO13 is the same. acting on the n0, which is pointing is the time direction. So all of our normals is just given by the SO13 rotation of the time. And this, from here, we can already write out what is the group element of this SO13. And that's the solution of our critical equation. And the smaller z can also be solved from this relation, because now capital Z is given by the Cassé, which is also the boundary data of the boundary tetrahedron normals. If I have time, I'll tell you details how to reconstruct the spin-form critical data from any given geometry of the four simplex in the next lecture. But here, what you need to know is that the spin-form critical points correspond to the four simplex geometry. But this is only real critical points. What happens for the complex critical points, as we said, we don't have this condition anymore. So it's not four simplex because its boundary is not a tetrahedron. If its boundary is tetrahedron, we have a conormal because tetrahedron is 3D. So we have in the 4D, it has a normal for the 3D subspace. But for this point, for the complex critical point, we don't have this normal, which means somehow it breaks the simplicity constraint for the complex critical point. And the simplicity constraint tells you it's equivalent to have a conormal of the 3D subspace. So this is the signature of the weak imposition of the simplicity constraint, because we have it at the classical level, but we don't have it for the complex critical point, which is a quantum thing, not a classical thing. Because all these complex critical points will not dominate the path integral. The path integral is dominated by the real critical point at this level, which is the classical thing. Okay, this is one thing. So we see we have some very simple equation motion which have the geometric meaning. It's a parallel transport, and it's a closure. The first one is parallel transport, the second one is closure. And this forms a four simplex. But there is one subtlety, is that now if you remember our bar vector, this B is nothing else but SU2 transform the sigma 3. Sigma 3 is a polymatrix. And we know polymatrix has the properties Hermitian matrix. And SU2 transformation doesn't break this property, so we have B. B is equal to B dagger. And then if we take dagger to the parallel transport equation, what we obtain is a new equation, and we replace the dagger with itself. So we see this gives you another solution. Why is another solution? So one solution is GVE, another solution is GVE dagger. And we know this G is SL2C, it's not SU2. So G and G dagger, they are different solutions. So when we have one solution, we always have another solution which solves exactly the same equation motion. So, and it turns out that these two solutions correspond to different orientations of the four simplex. So orientations in this means how we calculate the, so it's related to the signature of the volume if we want. And it turns out we can calculate the critical action. So it's basically the action evaluated at the critical point. We call it x0, which is the solution of our equation motion. And what we found is these two things. So for one solution, it gives plus I GF theta F. Theta is the dihedral angle, which is defined as the arc coach of the normals. So, but we have another solution which gives you exactly the same thing, but with the minus sign. So we have two contributions because we have two critical points, and they are all the dominating ones because their real part are 0. They only contribute to the phase as a critical action. So these two contributions, so if we only have one contribution, if we don't have this one, for example, and this is nothing else but the Regge action. But since we have two, it's not exactly the Regge amplitude. We have the so-called cosine problem because we have two configurations. And this is somehow the cosine problem, as we already said a little bit in Francesca's lecture. Okay, so basically this is the critical action tells you it's, you have two contributions. And why it's a cosine? Because if you calculate exactly what is n minus is the dagger of the n plus, and then you can write it as the cosine. Okay. But there one more thing. We didn't, it's only for single vertex, we didn't talk about the internal faces. So if we have a very large triangulation with many vertices, we have the internal faces. Remember, for the internal faces, J is also a variable, so spin is also a variable. And then we also need to do a variational principle to the spins. And what it gives us is that since this critical action is linear in spin, so the equation motion is simply this theta f, which is dihedral angle equal to 0. And what means what dihedral angle equal to 0, I think Bianca will tell you more about this in the radical calculus thing. It means all the geometries are flat geometries. This is not what we want because we know gravity is not flat geometries. Topological field theory is flat geometries. This is long-timely known as flatness problem. And now we know it's not a problem now because this is resolved by the complex critical points. For the real critical points, we have flat geometries, but we have complex critical points which are very close to the real critical points, and they are also contribute to the amplitude. And this complex critical point will give you the curved geometries, which is gravity. Of course, the complex critical points is more difficult to determine. It's not like the real critical point, we have a clear geometric median. No, we don't have this clear geometric median. And we really need to solve this equation motion. For real, we don't really solve it. We just write out its corresponding for simplex geometry. Now we really need to solve this equation motion. Of course, we also have the third equation motion, which is given by the variational principle of the spins. So in general, it's very hard. As I said, it's also polynomial equations, but with very high order because for single vertex, we have 44. And for a simplicial complex, we have hundreds or thousands of equations. And to find all the complex critical points is generally impossible. I mean, you can do it, you can try to do it, but it's really hard. But luckily, when we have complex critical point, which is really close to the real critical point, we can use Newton's method. We start from the real critical point, we try to use the Newton's method to find the complex critical point numerically. So this can be done. And maybe I'll tell you a little bit more in the third lecture when we use the example. But here is basically the ideas. Okay. This is basically, so when we have the saddle point approximation, we also know we can do the perturbative expansion around the saddle point. It's given by the Hongguang theorem. Everything can do analytically. I don't want to show these things here, but you can find the concrete formulas in the references. Let me check if I find, yeah, in this paper. For all the high-order calculations, you can follow the Hongguang theorem to calculate the first-order correction, second-order correction, third-order correction, and also the propagators, for example, which combines the second-order corrections. Okay, so all these are a standard method is basically to find the approximation of the integral, of a highly oscillating integral. It's called asymptotic expansion. And if you want to expand it, we also have the Harper asymptotic expansion. But these are all well-defined mathematical tools to do things, to do this approximation of the integrals. Because now we are on the lattice, we have the well-defined lattice path integral. Well, if you want, you can call it integral, not path integral, because it's really the multidimensional integrals. All the stuff we need to do is the asymptotic expansion of these integrals around the real critical points. But now we have a new question. Can we do this non-perturbatively? because all the saddle point approximation of the Hongguang theorem is a theory expansion of the integral. One question is, can we do it no perturbatively? Can we summing over all these perturbative series? You know, somehow, usually this perturbative series may not converge. We have we needed to use the resummation theorem to resum all the terms. But let's not talk about that. Let's see how we evaluate these high oscillatory integrals. And there is a method called Loops' symbol. So what is the Loops' symbol? Let's first do a 1D example. So how we integrate out a highly oscillatory integrals in 1D. We know we have saddle point approximation, but we have more things we can evaluate no perturbatively. We know what we used also in saddle point approximation is that we deform the contour. And this is how saddle point approximation works. So suppose we have an integral on the real axis. So so suppose we have an integral which defined only on the real axis. We know we can deform the contour if it's an analytic function. If the action is an analytic function, we can deform the contour into the complex domain. We have the Kersey theorem tells you this. If we have the same convergence region, these two contours, they are the same. But when we deform the contour, there is one contour is very special. It's the steepest descent contour passing through the saddle point. And it tells you that in the steepest descent contour, so this is a complex integral, but in this contour, the imaginary part is constant, and the real part is decreasing. Here is the real part is larger or equal than 0, for example, and the imaginary part on this contour is a constant. So this is also the stationary phase approximation if the real part is constant. So in this integration is only, so we don't have this sign problem which basically said that we have an oscillatory integral. Now on this contour, the integral is no oscillatory. That's why we can easily integrate it out, because when we have oscillatory integrals, it's hard to integrate it out, even numerically. So this is how we deal this in 1D. And Loops' symbols is basically the idea generalize this, generalize these ideas into multidimensional. So what happens is we have critical points, and again, we deform the integral curve. But now this is not only 1D, it's multidimensional thing. So how to find the equivalent integral curve for this multidimensional thing? This is told by the Picasso-Lipschitz theory. Basically, it tells you that the integral curve that equivalent to the original Rn integral in the complex plane is given by the so-called Lipschitz symbols. And the Lipschitz symbols is the equivalent class of the deformation of the real domain of the integral. And there are two things. First is the Lipschitz symbol, which I write this capital F, and there is n sigma, which is the weight. So it's a number. It's a number that tells you how these symbols contribute. And finally, the integral on all the symbols weighted by this n sigma is equivalent to the original integral. So the complex plane integral is equivalent to the original real plane integral. That's the idea of the Lipschitz symbols. And the idea behind it is, again, we chose the critical point, and we chose the similar things for the steepest descent path. And now it's given by these symbols. And in these symbols, we have the imaginary part of the action is constant, and then we don't have any oscillatory to our integral. And when we do not have any oscillatory, we can easily integrate them out, for example, using the Monte Carlo method. And that is exactly what we want to do. And now that how to determine these symbols. As we said, the symbols is just the steepest descent path, and we can write out the equation for the steepest descent path. And it's given by this equation motion. If you separate it into the real and the imaginary part, you can see, so for the real part of the action, it's a gradient flow from here because both are negative signs. And for the imaginary part of the action is Hamiltonian flow. Why is Hamiltonian flow? Here is plus, here is minus. So this z, the real part of z and the imaginary part of z is like the conjugate pairs, which originated from the imaginary part of the action. So it's Hamiltonian flow. The Hamiltonian flow means this SI, which is the imaginary part of the action, is a conserved quantity. So it doesn't change along the flow. So this is exactly our idea. We want to have a constant imaginary part, and we want to have a decreasing, here is increasing, sorry, because we have a minus sign. So we want to have an increasing real part, constant imaginary part. That's exactly the steepest descent passes. And you can do this in 1D. You check that is exactly the thing given by the stationary phase. And as I said, after that, we can approximate each integral on the symbols written as only the real part of the action. And the imaginary part is the constant. We don't need to integrate it. We can just put it out. So this now becomes the integral only with the real action, and it's decreasing. But okay, we have the flow equation, but there is still some problem. Let's skip this since I don't have a lot of time. One problem is for any given point, if you check the flow equation, we need infinite time for the flow equation flow to the critical points. So this means, okay, I mean, analytically everything is fine, but practically we cannot determine it in finite time. That's what we can do in numerics. I mean, we need finite time. We cannot do infinite time. So it means when we do numerics, we need approximations. So the approximations is given by the following. So first, since we have a exponential decaying integrand, when the SR is really large, the exponential is really, really small, so we don't need to consider them. So we don't need to consider the whole symbol. We only need to consider the symbol up to some time. That's a finite time approximation. This is the first approximation, which we approximate the symbols with some g hat. G hat is the cut of the symbol. We only integrate part of the symbol, which we ignore the contribution where SRZ is really small. For example, smaller than some large number. I don't know. It's given by your numerics. Okay, and now we also need another approximation. So as I said, critical point is what we know usually, and the critical point is a saddle point over the flow. It doesn't flow actually for the critical points. Critical points doesn't flow under the flow equation. Only other points flow. So we also need another approximation which we can generate the flow because we cannot generate the flow from critical points. So we can only generate the flow on a small region, which is I call this V sigma around the critical points. that's the region we can generate this flaw. So this is another approximation, which we generate the flaw not about the critical point, but the flaw of a region which around the critical points. And this is also approximation, and this is well approximate. This will well approximate the original symbol if this V sigma is really close to the saddle points, the critical points. So here we have two approximations. The first approximation is we fix a small region around the critical point, and it will generate a flaw which we call f hat sigma. And then we flaw only on finite time, which is I call this tilde. So this is the finite time flaw, and so there are two approximations. And of course, when we generate this flaw, we use the steepest ascent flaw. It's the reverse of the steepest descent from the infinity. So this is some practical thing we need to take into account besides the analytic thing. And now we have another problem. Because now we approximate everything using V sigma, we need to determine the measure for the integration. This tells you how to define the measure. The measure is actually determined by the steepest ascent equation, the linearized steepest ascent equation, because we are very close in this region. And it's actually given by a Hessian matrix. And this Hessian matrix is the second order expansion of the action, if you want. And the Hessian matrix, if we write it as a complex matrix, because at the critical point it's complex. So we write the real and imaginary part, and we can write out the eigenvectors of the Hessian matrix. And it turns out we always have even number because we have the real and the imaginary part. It turns out we have n direction. If it's n-dimensional integral, we have n direction which is attracting. So this is basically the steepest descent flaw into the critical point, and we have n expanding directions. So of course we approximate everything using the expanding, because then it flows out, generates the symbol. So what we need to do is to find out these eigenvectors, which is given by the eigenvectors, which are called rho I, corresponding to the eigenvectors, corresponding to the eigenvalues lambda larger than 0. That's the thing generates a flaw. And that gives you exactly what is the region I used to approximate my critical point. And also we can write out what is the measure, which is the Jacobi matrix between the x defined here, which is linearized around the vector, and also the original variable for the steepest ascent flaw. But this is also a function of time, so it also flaws, this Jacobian also flaws when we flaw with the time. So we have the flaw equation also for the Jacobi, and that gives you all the ingredient you need to have to calculate the symbol. And with this, we can write out the final approximation of the original integral. And now it's no perturbatively given by first the imaginary part, and this is approximated symbol. So this integral is on this approximated symbol, which we have the Jacobian flaw and also the flaw of the symbol. And it's all determined by x, which is a coordinate on a plane around the critical points. So basically, we transform the original integration into an integration on a region around the critical point. And this region is given by the positive eigenvectors of the Hessian matrix. Okay. One more problem is, as I said, so for integral, now we don't have any we don't have any oscillation. In principle, we can use Monte Carlo method to calculate the integral. But now there is a problem, because when we use the Monte Carlo method, we need to know the volume. That's how we use the Monte Carlo method. But now we don't have the volume, because it's very hard to estimate the region, the volume of this V sigma region. So this put another problem to do numerical calculations. But luckily, for observables, we don't need to estimate the volume. Because observables, here F is something about the observable. And when we calculate F, we divide it by the original transition amplitude. And the volume cancels for the numerator and the denominator. So for observables, we don't have the problem with the Monte Carlo. And this is exactly, if you look at this formula, is nothing else, a sampling problem with the effective action given by the effective action on the symbol. And this is real because it's on the symbol. We already put the imaginary part out, and it cancels exactly the denominator, and we don't have any imaginary thing. So this basically defines a probability distribution which weight our observable. So we can use the Monte Carlo, the Markov chain method, or the Metropolis method to symbol our observables, which is F. So finally, we know how to calculate no probability with the observables, even we don't know how to calculate the transition amplitude because we cannot estimate the volume. So I have a concrete example of the Markov chain Monte Carlo method. I don't know if some of you already know this. So it's a statistic. It's coming from the statistic models. So Markov chain is basically something satisfies the Markov property. So what is the Markov property? Is this property? It says that, so we have so this is the chain, start from the first step to the t step. And it tells you that the probability to find something at the t plus 1 step is only determined by its previous step. So it has no memory to the all previous steps. So all steps beyond the previous step, it has no memory about them. This is the Markov property. So basically, from here we can define a transition matrix, which is the transition from the I state to J state from the step t minus 1 to step t. And why this is a good thing to have this, Markov property is that for no periodic Markov chain, you can show that when t goes to infinity, we have a stationary distribution. So it means that it converges to a distribution. And this converged distribution, we call it pi j. It means it doesn't change under the Markov chain. So we have a certain stationary distribution, which after sufficient longer time of evaluations, we are in a good approximation of this distribution. And this distribution is our target distribution, is nothing else but this probability distribution used to evaluate our observables. And if we have a sample of this distribution, we know how our observable is sampled on this distribution. So now the problem becoming a reverse procedure. So we already know the target distribution, how we build the Markov chain, how we build the P, the transition matrix. That's the Markov chain Monte Carlo method. And this method is based on a condition called detailed balance condition. And this is, as said, is a sufficient but not necessary condition for this pi to be stationary distribution. So for any stationary distribution, we have this property. But now the transition matrix satisfying this relation is still unknown. Okay, thanks. I think I still have 10 minutes. Let's speed up. Okay, so to solve this problem, what we have to do is to introduce an extra acceptance rate. So we decompose, we write this P, so we can introduce any answers for P. So we introduce answers such that P is equal to alpha multiplied Q. So now this detailed balance condition becoming this. And now we can solve out what is alpha. Alpha is given by pi multiplied Q. And then we can give answers for Q. A very easy answer is that we take Q to be symmetric. Here we just using a very special thing to increase the accept rate. Otherwise the alpha is somehow called acceptance rate, may be very small. So this is like a renormalization procedure. So we take the minimum value between this one and this and 1. So pi is our target distribution we already know. And if we take Q to be symmetric, the acceptance rate is nothing else but the minimal values between the t minus 1 step over the distribution between J states, so the probability between the J state and the R states, the ratio between them. So this is a calculable acceptance rate, and it's well defined. It's basically given by our exponential probability distributions. So this is how we do the calculation, at least algorithm, and we can use, there are many techniques to optimize the procedure, but this is the basic ideas. Yeah. I think I'll tell you details with a concrete example on the next lecture, which we have the numerics, exactly. Yeah, and I think I'll stop here. This is basically a summary of what we need to do to calculate observables with different symbols, no perturbatively. And I think we have 10 minutes, so if you have questions, we can take some questions before we move to the next lecture. It will be on Friday. By the way, so the numerical code, I try to do it with Julia and Python, but some package is written in Mathematica. But I know many of you may not have a license for Mathematica. That's why I'll try to do it on Julia and Python. So, and I'll upload all the numerical notebooks on GitHub and send a link to you so you can follow every procedure for the next lecture. Yeah. Yeah, that's all.
Okay, so if there's no question, then we can close the session. Yeah, we have.
Yeah.